Hello, and welcome to Nikki's Dad Talks About Physics. So, yesterday I was helping Nikki with her physics homework, and a couple of problems came up that I'd like to take a few minutes to discuss to help Nikki and her friends figure physics out a little bit better. So, one of the problems involved a child sliding down a slide from a certain height, and the question was, what is the velocity at the bottom? Now, Nikki knew that at the bottom of the slide, the child had kinetic energy, and she understood the concept that you start with a potential energy due to gravity at a certain height, and as you go down the slide, the potential energy changes to kinetic energy. And if you know the total energy you started with, and assuming it all turns into kinetic energy with no losses due to friction or anything, that you can calculate the velocity at the bottom of the slide by simply working out the equation E equals 1/2 mv squared, which is the equation for kinetic energy. So potential energy, E equals mgh, converts to kinetic energy over here down at the bottom of the slide. There we go. Okay, from mgh down to 1/2 mv squared. The problem Nikki hit, of course, was she didn't have the mass. So she wanted to calculate from the energy equals 1/2 mv squared, but where's the mass? And this was a fun problem I used to give to my physics students. So I enjoy teaching it to Nikki, and I'll describe it to you. Now, I'm not going to do this on paper or with a whiteboard. I'm just going to describe it and talk about it. And this is something that as good physics students you should get used to, is just using your noggin, your head, your brain, and get used to thinking through equations that way. So let's go. The potential energy is mgh, and the kinetic energy 1/2 mv squared. So you can't solve this with one side or the other because you don't have the mass. So what you've got to do, you have to set the equations equal to each other, because the total energy in the system remains constant. By the way, that's a law called the conservation of energy. And so the energy remains constant, and so you can equate them. So you say mgh equals 1/2 mv squared. Okay? And you equate them together. Now, once you equate them, you have to solve the equation. So that means you've got to isolate the velocity on one side of the equation. So the first step, since it's mgh equals 1/2 mv squared, I got to get the 1/2 and m out of there. So the first thing I'll do, I'm going to multiply both sides of the equation by 2. So now I get 2mgh equals mv squared. Now I got to get rid of the m, and this is where things get interesting. When you divide both sides of the equation by m, what happens? I have 1/2 mv squared, I have mgh. When I divide them by m on the bottom, those m's, they both cancel. And this means that the mass has no effect on the velocity of a falling object. Now, of course, this is based on a frictionless system. Go away, Quentin. That's Nikki's little brother trying to come in here and bother me. He does this a lot. Bothers Nikki sometimes too. Okay, so mass is canceled out. And this is something that Galileo Galilei figured out in the 1600s, 500 years ago. Galileo actually figured this out. And he was basically changing the science of Aristotelian sciences by exploring acceleration, which the Greek philosophers and scientists had never really talked about. So the mass cancels out. And now you're left with 2gh equals v squared. Take the square root of both sides, and you can solve the equation. And you never, ever needed the mass. So that was very fun to show to Nikki, and hopefully it's going to help her on her exam. Hopefully it'll help you on yours. So remember, just equate the potential energy in a complete conversion to the kinetic energy. Mass cancels, you won't need it. Now, in real life, we know it doesn't quite work like this. Bigger children, when they go down the slide, go down slower. And the reason is because something called the force of friction, which is related to the normal force, which, because the normal force is offset and perpendicular to the angle of the slide, means that heavier objects have a stronger force of friction, and therefore they go slower. So, you can see why the Greeks were a little bit confused by this, and Galileo's ideas kind of turned things upside down, because the observation in the real world is that different masses fall at different rates. But that's due to friction, and that'll be a discussion for another day when Nikki gets to it. Have a great day. Bye.